Hi, my name is Jiang. I'm currently a master's student in Agriculture and Biological Engineering department at Purdue University. I'm a member of Dr. Jiang Falkenberger's research group. My research focuses on nitrate flux in the rivers. More specifically, I estimate nitrate load in tile-drained agricultural watersheds. Subsurface tile drainage is a common agricultural practice in the Middle West. It places pipe at certain depths below the soil surface. Tile drainage improves the productivity of poorly drained soil by lowering the water table, providing a better environment for crops to grow. However, it also changes the balance among different flow paths and greatly increases nitrogen loss that cause many water quality problems. Particularly, the increased nitrogen loading from Middle West was found to be the primary cause of large-scale hypoxia area in the Gulf of Mexico. Currently, although nitrogen leaching from the tile drainage has been well studied at the field scale, little is known about its impact at the watershed scale, while most conservation management strategies are required to meet at the watershed scale. The goal of my research is to develop a conservation tool to predict nitrate based on drained watershed characteristics and evaluate the role of tile drainage in delivering non-point source nitrate. To do this, first, I estimate the point source nitrogen load using reported municipal and industrial wastewater discharge, which is a small part of total nitrogen load. And then, to estimate the non-point source nitrate, I analyzed its transport mechanism, and based on data availability, I selected the tile drainage percentage and cropland percentage as two important predictors. I evaluated a range of regression model combinations and finally selected the model that most balanced the prediction efficiency and the structure simplicity. I developed annual model, monthly model. Also, I use this model to predict long-term average nitrate in regions with different drainage water characteristics in each season. Finally, the model was tested in 10 additional sites, and it performed well, especially for highly drained watersheds. The study results show that tile drainage play an important role in delivering nitrate into rivers. More than 70% of the non-point source nitrate loss in a watershed could be attributed to the tile drainage in intensively drained agriculture area. The results also suggest that implementing effective agriculture conservation practice is critical to achieve the total nitrogen reduction goal. However, how are we confident with the model predictions? Since uncertainty is inevitable in water quality modeling process, there could be varied, even very high uncertainty in the estimated nitrate loads. If so, that will greatly affect the model output and the effectiveness of conservation management decisions. So, in the second part of my work, I quantify the overall uncertainty in estimated nitrate load, combine the data measurement uncertainty and load estimation uncertainty. This work obtains a distribution of uncertainty for a range of scenarios using different methods, sampling strategies, and for watersheds with different characteristics. So the researchers and managers of watershed conservation projects can refer to these results to get idea about the average error or maximum error, minimum error of the modeled nitrogen loads. To summarize, my research includes water quality modeling, specifically estimating nitrate load at a watershed level and associated uncertainty, to better inform conservation policy and practice. This information can ultimately be used to facilitate watershed conservation work in several ways. First, it will help identify nutrient source in watersheds. Second, it can facilitate developing total maximum daily load program, regulate the total amount of pollutants in rivers and streams. Finally, the developed model is also a simple yet effective tool to assess the potential effectiveness of management practice. Thank you.